All right, let's try number one. Number one says shows three situations where the positive charge particle velocity v moves in a uniform magnetic field, experiences a magnetic field of FB. In each situation, determine whether the orientations of the vectors are physically reasonable. Okay, so I've got a velocity this way. I've got a magnetic field in the board. So which way would the force be?
To the left.
Whoop. It would be, you know what? It should be perpendicular first. So it's going away.
The angle component of the velocity doesn't matter. It's just the vertical component.
Right. Right, but the force would still technically be in this direction. But if that's straight into the board, and this is the actual direction of the velocity, that would be the force would actually be that way. Does that make sense? V, B, F, right? Right hand rule.
So this isn't physically reasonable?
So I would say that's not. I would say A is not, although it's darn close and kind of suspicious looking. Let's try B. Well, I'm feeling what you're feeling. I'm like thinking I don't know if B is going to work either. I don't know if C is going to work. I'm wondering if this is a bad problem. I don't think so because I've done this problem before at some point, I hope. Okay, so I've got V. V's in this direction, right? I'm curling towards B. Which way would my force be? Out of the board. That one actually is legit. So B's okay. Right? And then C, I've got magnetic field this way. I've got the force this way. My velocity is coming out my forehead. So V, fingers out, angle that way. I still think that would be a component more that way-ish. So I would say B is the only one that's legit. Does that make sense?
Wait, can you go back to A?
Yes, A. Okay, so A is V is this way, velocity this way. Magnetic field into the board. So I stick out my thumb and I'll get a force in that direction.
Velocity's this way.
Velocity's this way.
Into the board.
Into the board. So I stick out my thumb. It's be perpendicular to this one, right?
But it's not perpendicular.
Yeah, right. The picture is not perpendicular, so therefore I would say no. It's close. Their force vector is this way, right?
Yeah.
I would say there's enough difference there. I would say that I would disagree with them saying that is in the same direction.
Okay.
I don't know if I'd bet money on that's what they meant to say, but B definitely works. So that makes me feel better with the whole thing.
B definitely works?
Yes, because V is this way. I gotta curl my fingers towards B, so I turn it like this. I can curl my fingers towards B, stick out my thumb, straight out of the board. That's what that dot means, straight out of the board. But you don't do F. You're gonna do velocity, which is out of the board. Magnetic field this way. So my thumb would be sticking out that way. So it's slightly off of what they drew.
Okay, wait, you chop on velocity.
No, velocity is the direction my fingers are pointing. Magnetic field. Curl my fingers towards the magnetic field, stick out my thumb.
But it's a V cross B, right?
Right. So V first.
So V first.
Then curl my fingers towards the direction of B. Stick out my thumb. I think that would be perpendicular to that one. So therefore I wouldn't accept it. Good? Okay. 2. Should we do 2? Is 2 a problem?
Yeah.
All right. These are good problems for you guys to do, though. Let's do 2. Here we go. I've got A. B is 2 I hats minus 3 J hats. B is equal to 4 K hats. For each of 4 situations of the velocity v of the proton in a certain instant in which the magnetic field. Without written calculations, rank the situations according to magnitude of greatest force on a proton. So I want the greatest, so magnitude, right? So I want most perpendicular, right? So here I've got 3 I hats plus 2 J hats, and I've got a K hat again. Minus, doesn't really matter, it's just a direction thing. I've got velocity equals 3 J hats minus 2 K hats, and then my magnetic field is 4 I hats. And then I've got velocity in this direction is equal to this, which is 20, and over here I've got 4 I hat. This is I hat as well. So first of all, what's the force of this last one? They're not perpendicular at all, so there's going to be a big 0 there, right? I can't read my own writing. Was that an I hat after a J hat? That's really annoying if they did that. No, it's
That's
K hat.
okay.
Okay. So this is a K hat. This is a 2 and a 3 in the I and J directions. And these are both in the K directions. So these are going to be the same, aren't they? And these two are perpendicular to this one. So these are 3 and 2 again and 4. So what is all these going to add up to? The same, right? Same.
Really?
Yep.
D.
Not doing any math, they are the same. It's interesting that they didn't give me one that was different. But as long as these two are perpendicular to this, these two are perpendicular to this one over here.
Why'd you write 0 next to D?
Because these are not perpendicular.
Oh, yeah.
So how much net force would I have? 0, right? If I'm traveling in the direction of the magnetic field, I get nothing. Magnetic field means nothing to me. So far so good? All right. Let's try 6 then. 6, I have this, followed by a this, followed by a this. This is B. Here's A. I'm going this way, and I make a curve this way. That's C. I'm going this way. That's D. I'm going this way. That's E. And then I go this way, and then whoop, and then I've got 2 plates sitting in space, and something weird happens while I'm in the plates. And I curve this way. Okay. Figure 2928 shows a path of a particle through 6 regions of a uniform magnetic field. Oh, I missed my F. Here's an F right here. So there's an F curving this way, right? Okay. Magnetic field. Where the path is either a half circle or a quarter circle. Upon leaving the last region, the particle travels between 2 charged parallel plates. They're deflected towards a plate of higher potential. And which direction of the magnetic field in each of the 6 regions? Okay, so I'm deflected towards the one with a higher potential. What does that mean? Does a higher potential plate have it? The other one does not have.
Or positive.
It's more positive, right? It's harder to get to it, right? If you have a positive test charge. So this is positive, and this is negative. So what does it tell me about my charge?
Negative.
It's negative, right? It's repelled from the negative and attracted to the positive, so therefore it is a negative charge, which is going to make every single thing we do backwards. Isn't that nice? So, yes.
Is that the only purpose of the plate part?
Yes. They're trying to tell you that the charge of the thing is a negative. It's probably an electron, but we don't even know that. Okay, so particle shoots in here. It's got a velocity in this direction. Which way does it feel a force? Force this way, because we're talking about centripetal force, right? So if my force is that way,
Arm bender.
it's perpendicular, right? So it's perpendicular. So I go V. Is B into the board?
Yep.
If it's into the board, my thumb would stick out that way, wouldn't it? It's not into the board.
Well,
Oh, yeah. Okay, yeah. You got the electronic taken care of? Back to negative. Or you taken care of? Okay, good. All right. So this would be in the board. So normally it'd be that way. But since it's a negative, that would push it that way. So therefore, into the board is what we got. So we got it into the board here.
What?
Okay, so this way, magnetic field in the board would normally shoot a positive charge this way. It's a negative charge, so which way would it go?
It's going this way.
Okay, it's traveling this way. Which way, magnetic field, you said the force this way. It's going to be in or out of the board, right?
But don't you feel the force this way, so you turn it this way?
Okay, my thumb's got to go that way when we're done, right? So if I do this, a positive charge would go this way, agreed? The magnetic field was out of the board, it'd be this way.
I thought you did V and then F and then V.
No, it's V cross B equals F.
Oh, shoot.
So V, B, F, and because it's negative, it flips.
wait a minute. Wouldn't the magnetic field have to be the same everywhere because it says it's uniform?
It says uniform in the region.
Oh, okay.
This is why it makes a semicircle a half circle. If it's different than uniform, it would make weird circles. Okay?
Yeah.
All right, let's try the next one. Where's B? B's down here. So I'm traveling this way. I have a force this way, right? So my fingers go that way. Magnetic field into the board would cause it to go this way if it was a positive charge. So that's the wrong direction. So it can't be in. It's got to be out of the board. Go ahead and do C. See if you got it. You got it. Yes.
Do we only use the second right-hand rule when we're dealing with the current through a wire?
Current through a wire, which way the magnetic field is operating at that spot in space. That's only way we use it. Shouldn't even be a right-hand rule. They should make that one a left-hand rule just to make our lives better. But they didn't. And one thing sinister happening to the problem. All right, so whoop, whoop, whoop. So it's got to be out of the board, right?
Yes, sir.
Right? Are we good with that one? Okay. Of course, that way. Boop, boop, boop. So that's got to be in the board. Yeah. Okay. I'm going to skip E and do F.
Am I gonna skip E?
Okay, I'll do E. Out of the board. Ah! Two people said no. All right, so normally if I'm traveling this way,
Yeah.
magnetic field would into the board would cause my force to go that way, but because I'm a negative test charge, it's going to go the other way, so it's going to be out of the board.
But then
Right, you're wrong.
Wait, wouldn't it be,
I
since
said,
it's traveling to the right,
It's traveling this way, so my finger's this way.
yeah.
If I put it, and the force is going to be downwards, agreed?
that's it.
Okay. So if I'm going this way, I have a magnetic field into the board.
Yeah.
If I had it into the board, it would cause a positive test charge to go this way.
So it has to be in.
Oh, you're right, I did. I've got it wrong. Thank you.
Okay. I thought you
I double
were
negative.
arguing the input. I'm like, wait, why am I arguing the output? Because I had N on my paper.
That's circle across it.
Yes, that means in. Did I do it wrong the second time?
No,
That's
you're
good. All right, so you guys are correcting me, so I think you got it. All right, let's try number 7. Try number 7. Based on roughly the same principle.